in last lecture we were discussing about the string efficiency. So here this is the tower part, and which is actually connected to the ground, and this part is the cross arm. Okay, so totally it is mentioned here the tower. So this is tower, and again I repeat, this part is connected to the ground or earth. Okay, so we can say that this is at the ground potential. So obviously, as the tower itself and the cross arm that is connected with the ground, so this is also having the ground potential. Okay, now here in this example, three insulators are connected. Uh, so the topmost insulator, this one, the second one, this one, and this is the last one. Three insulators, and here we have the conductor. Now, ideally, the voltage distribution across each conductor, each insulator should be same. Okay, so that means this is V1, okay, and this is V2, and this is V3, which is also shown in this diagram also. Okay, so ideally this should be same, but practically these are different. So it is mentioned here that V1 not equal to V2 not equal to V3, and the reason that we have discussed in the previous lecture why it is not same. Okay, actually V3, for this case V3 is greater than V2, and that is greater than V1. Okay, so the voltage across the insulator nearest to the conductor having maximum voltage. Okay, so this P point, Q point, and this R point, these are the metallic contact of the insulator. Okay, and the current is flowing, these are not desired current but still flowing from this conductor to the tower, and we know that tower having ground potential again. Okay, so string efficiency, so that is actually the voltage. So basically this is the string of this insulator, so the voltage across the string, so obviously voltage across the string, that is this V, that should be equal to V1 plus V2 plus V3. Okay, obviously the voltage arises across each insulator, that equal to V, and that is the voltage across the string, and here the string is the string of insulators. Okay, so this is the string, or here this case. Okay, so that divide by voltage across the string divide by n is the number of discs in the string. So here in this example we have three discs or three insulators. Okay, so number of discs here is 3. Okay, and the voltage across the discs nearest to the conductor, so nearest to the conductor, voltage across the disc is this one, nearest to the conductor. So this voltage is the voltage nearest to the conductor. So obviously from this expression the string efficiency can be expressed for this case V divided by number of discs is 3, and voltage nearest to the conductor is V3. Okay, so this way if we have 6 discs string, so then for that 6 discs, sorry, for 6 discs we have this efficiency as the string voltage divided by number of discs is 6 into V6 nearest to the conductor. Okay, now go to the next slide. So the mathematical expression, so this is the physical system, and that is the equivalent, second diagram is the equivalent system. Okay, so again tower having ground potential, so always we have to remember that that is at the ground potential, otherwise some confusion may arise. Okay, so the mathematical expression for this system. Achha. So we have 3 point, first of all 3 point P, Q and R, and remember this is the metallic part of that insulators. Okay, now applying KCL to node P. So if we consider node P here in the equivalent circuit, so look, current entering to this is I2, current entering to this node, current leaving from this node are I1 and IC1. So here it is to know na, C is the self capacitance and C1 is the shunt capacitance. Okay, so this capacitance C arises between between this cross arm and the metallic part of the insulator, that is here. So this is the cross arm part and here is the metallic part. Okay, again with this metallic part, the Q insulator metallic part is connected, and here again we have another metallic part here, and this one conductor itself a metal. Okay, so again we come to the KCL point. So for if we consider this P point, so here current entering is I2 and leaving currents are I1 and IC1. So we write this expression. Now replace all this current in terms of their voltage and the reactance. So I2 current, basically the voltage, I2 comes here, na, I2 is here. So the voltage is here is V2. So V2 voltage divided by XC. Okay, so X is the expression of the reactance of this capacitor. Okay, this capacitor reactance is XC. So putting this one, similarly for I1 and IC1 we have this expression V1 divided by XC plus V1 divided by XC1. Okay, so why this is V1? Look, I1 current is here, I1 current is here, and its corresponding voltage is this V1. Okay, and similarly for IC1 current is here and its corresponding voltage, remember this P point and this tower part, that ground potential. So if for the topmost disk, this disk, the voltage between this ground and point P is V1. So obviously if we consider this P with this ground, this the same ground, so this P and this ground, the same voltage is there, so that's why it is also V1. So this point and this point having V voltage, so this point and this point is same, both are at the ground potential, so this point and P again V1. So that's why here also we have V1. Okay, so now put the value of XC. X is nothing, we are just ignoring the X equal to this part, means 1 by j omega c, this part. So just put the value omega c directly here. We are ignoring the imaginary part here because left hand side and right hand side, both the cases there is the j, so j is common. So now eliminate all the other common parts like omega and c. We are removing this omega and c. So finally we have this expression. Okay, so that is mentioned, that is as equation 1. So from there we can also have the expression of V1, that is V2 divided by 1 plus m. That is also true. Okay, and remember we have this expression, this small m, from where it comes. Actually we are replacing capital C1, that is nothing but your shunt capacitance by this MC1. So M is nothing but C1 equal to MC, so obviously M is nothing but C1 by C. So M can be controlled by adjusting this capacitance value. Okay, so obviously M is adjustable parameter and it's a constant for a particular system or particular design. The next slide. Now same way, the same way, in previous slide we have applied KCL for the P node and now we are applying the KCL for the Q node. So Q node is here, this is your Q node. So we are applying KCL there. Again the same logic, the current entering to this node is I3, current leaving from this node is I2 and IC2. So these two. Okay. So just write this expression I3 equal to I2 plus IC2. So I3 current is here and its corresponding voltage is V3, that is between conductor and Q point. The V3 divided by its reactance, so that is nothing but XC, and we'll replace the XC by its actual value in terms of capacitance, equal to V2 divided by XC. From where it comes, look, I2 is the leaving current, one leaving current is I2, the corresponding voltage is V2 divided by its reactance XC, because this is C, self capacitance, and plus now this part is from where it comes, actually that is IC2. Now IC2 is replaced by these terms. IC2 is this current, IC2 is this current. Now look again, this is node Q to this point is nothing but ground, and the whole tower and cross arm, those are in the ground potential. So if this is ground, so obviously this point is also at the ground potential. So this node, this ground node and this ground node same. So obviously from this Q to this point, or from this Q to this ground, these are same. So this ground to this Q, what is the voltage between these two? V1 plus V2. So that's why here we have we can write V2 divide plus V1 or V1 plus V2, and the corresponding reactance is this Q to this ground, same now. So here we have the capacitance is C1, here we have the capacitance C1 equal to MC. Okay, so X C1. Okay, so here also C1 that equal to MC. Okay, and C1 equal to MC. This expression is always true, and M plays an important role to control the string efficiency. Later we will discuss. So that's why I am repeating this M term again and again. So M equal to C1 divided by C. Okay, M equal to C1 divided by C. So however, by putting all these values, now replace the reactances, okay, with its actual value, that is omega C, etc. So the common part should be eliminated, and now we have the final expression like this. So V3 equal to V2 plus V1 plus V2, first bracket closes, and then M. Okay, so now again separate the different terms of V1 V2, separate V1 V2, then we have this expression again, V3 equal to M V1 plus what happens here, look, V2 that is actually replaced by V1. From where it comes, we are just going to the previous slides. Look, the expression of V2 is nothing but V1 1 plus M. So V2 is nothing but V1 1 plus M. So put this V2 here, put this V2 value here. So we have V1 1 plus M whole square. Okay, so actually, so the expression is V2 1 plus M. So the put the value of V2 here. So we have V1 1 plus m into 1 plus m. So V1 1 plus m whole square. So just putting these values here. Okay. So now so 1 plus m whole square, that can be written as this. Okay. So finally we have taking V1 as our common part, and finally we have equation 2, equation number 2. This is our final expression, or in other word, this equation 2 can be expressed as V1 equal to V3 whole divided by 1 plus 3m plus m square. Okay. So we actually use equation 2 in both the way, this way or this way. Okay, same thing. Okay. Now go to the next slide here. So voltage between conductor and earth. This R node is nothing but this is the metallic part. This is actually is the conductor section. Okay, conductor part. So the voltage between conductor and earth. Okay, so this R and the conductor, these are same thing. So voltage between conductor and earth is obviously there is a string voltage, right? Voltage between conductor and earth. Nothing but this is your ground. This part ground. The whole thing is ground, or you can say that this is earth. Okay, you can say this is earth. So that is basically the string voltage. Voltage between conductor and earth is basically the string voltage. So that's why V equal to nothing but V1 plus V2 plus V3. So put those values. Now we have from the mathematical expression, we have the expression of V2 and V3. Okay, so put the values of V2 and V3 here. So V equal to V1 as it is, plus V2 is nothing but 1 plus 1 V1 into 1 plus m plus of V1 into 1 plus 3m plus m square. Okay, so this expression we already have. Okay, so from this equation 2 and from equation 1 we have the expression of V2 and V3. Just put those expressions here. So finally we have this expression. So also equation 3 can be expressed as V1 equal to nothing but V divided by 1 plus m into 3 plus m. Okay. Now from each expression we can write the expression of V1. So V1 with V2, what is the relation? So V1 equal to V2 divided by 1 plus m. From the previous expressions we have equal to V3 divided by 1 plus 3m plus m square equal to by this expression 3 we have V divided by 1 plus m into 3 plus m. Okay, so equation 4. So this is the most important relation. So if we for the mathematical calculation, it is not possible to always derive all these things. So roughly you have to remember these expressions so that you can solve the numericals easily. Okay, and now to the next slide. Okay, so therefore voltage across top unit is V1, this one. Voltage across second unit means second insulator is this one, and the third insulator is this one. Okay, so obviously if we have these expressions, so from there we can have our string efficiency again. So string efficiency is voltage across the string. This is nothing but V, okay, divided by n. N is how much it is, so V, that is written here, divide by n. N is number of discs is 3 into voltage across the discs nearest to the conductor, that is V3. The nearest to the conductor voltage is V3, and if we want to represent the string efficiency in terms of percentage, just multiply the value with 100. So we have some value, okay, some value that is in percent. Okay, and again number of discs, n is the number of discs in the string. Okay, and here that is the expression. This is the top expression because we have to deal with this expression. The V1 with the other Dix voltages and the string voltage, that is here equation 4, and string efficiency expression that is written again. Okay, for number of Dix is 3. Achha, now we can conclude few things from these expressions. Okay, so what are those? Okay, the first one, if m equal to 0.2, okay, we can assume any value, any constant value. So m equal to 0.2, then from equation 4 we get v2 equal to 1.2 v1. It's very simple to get. Equation 4, this one, equation 4. So put the value of m as 0.2. Okay, 0.2. So now here, so I just write the expression again. v1 equal to v2 divided by 1 plus m. So if we put the value 1 plus 0.2, so we have how much voltage we have. So v2 equal to 1.2 v1. So this way you can put the value in equation 4. Okay, so now we have v2 equal to 1.2 v1, right? And v3, similarly for the v3 expression, this part, if we put the value of m here, so we have this value v3 is 1.64 v1. Okay, so we have v2 and v3 in terms of v1, and from this it is clear that v3 is the voltage nearest to the conductor. Okay, this is the Dix voltage nearest to the conductor and having the maximum voltage, so maximum voltage across it. Okay, and the voltage across other Dix decreasing progressively as the cross arm is approached. Cross arm is approached means we are approaching to from v3, then v2 to v1. Okay, so v1 is the voltage across the Dix nearest to the ground or to the cross arm. Okay, so from this value, just putting a value of m equal to 0.02, we can see that again the conclusion v3 having the maximum value, then v2, and minimum value is appears across the topmost Dix, that is nearest to the cross arm, v1 having the minimum voltage. Okay, so here we have minimum and these we have maximum, right? Achha. The second point, greater the value of m, that is nothing but C1 by C, the more non-uniform is the potential across the Dix and lesser is the string efficiency. Okay, what does it mean? So greater the value of m is having greater value. So if C1 is increased now, okay, greater the value of m means C is more. Okay, effectively this ratio is basically more. Then the more non-uniform is the potential across the Dix, means the difference between V1, V2, V3 that increases as the value of m increases. Okay, so as the value of m increases, the difference between voltages of V1, V2, V3 to Vn, that is also increases, and that ultimately increases the non-uniformity of the potential across the Dix, and obviously that gives you lesser, that drops the string efficiency. Okay, so that's why it is written lesser is the string efficiency, so string efficiency drops. Again I repeat, for this case if the value of V3 equal to ideal case V2 equal to V1, if that happens, then what will happen? The string efficiency becomes how much percentage? So that is 100%. So our aim is to get more efficiency. So our aim is to somehow manage the voltages that should be very close, or the difference between voltages should be less or minimum. We have to manipulate the design, or we have to do something in such a way that the voltages are, it is not possible to get the voltage exactly equal, but we have to do something so that it is almost near, okay, almost near. Then we are approaching to the string efficiency towards 100%. 100% that is not possible, or actually not feasible, okay. So however, now come to the next point. Next point is the inequality in the voltage distribution increases with the increase of number of disks in the string. Obviously, as the number of, if we have 3 disks, n equal to 3 disk system, okay. So whatever the string efficiency, if that n becomes equal to 6, so then the variation of voltage distribution is more and more, or the non-uniformity or inequality in the voltage distribution, that is also more and more. So the string efficiency that decreases, okay. So this is the point. So the inequality of the voltage distribution increases with the increase of number of disks in the string, okay. Therefore, shorter string has more efficiency than the longer one. Obviously, if we have a single disc, a tower is there, a single tower, and with it a single disc, and with this there is a conductor is connected, current is flowing through the conductor, then what will happen? For this case, this is the ground potential, this is the conductor, so only one string voltage or the voltage across the disc is same, V equal to V1, okay. And so for the string efficiency expression, is the string voltage divided by the number of discs 1 into the nearest to the conductor voltage. So here the one disc, so V1, and this V equal to V1, so we have V1 by V1, so obviously 100. So if we increase the number of discs, so obviously the variation of voltage is there, and obviously string efficiency drops, okay. And method of improving string efficiency we will discuss in the next slide, means next lecture, okay. So